The irony became obvious by 1975. America's supposedly superior Quonset huts, built with better materials and modern engineering, were collapsing in farmers' fields across the Midwest. Meanwhile, British Nissen huts erected during World War I, 60 years earlier, still stood across Scotland and Yorkshire, still keeping sheep dry, still storing equipment, still refusing to fall apart. This wasn't chance. It was the inevitable result of a philosophical difference baked into the designs from the beginning. One structure was engineered to be improved, the other was engineered to be indestructible. And when decades of weather, neglect, and zero maintenance took their toll, only one philosophy survived. The fatal flaw hidden in American excellence. When Navy engineers at Quonset Point designed their hut in 1942, they made one decision that would doom thousands of structures decades later. They separated structure from skin. The Quonset used an internal steel framework, curved ribs that stood independently and carried all the loads, with corrugated panels screwed on as mere cladding. This seemed brilliant. It allowed for insulation, electrical integration, and interior modifications. It made the Quonset objectively better architecture. It also created a two-component system where both parts needed to survive for either to function. The engineering logic was sound for the intended use case. Military bases needed buildings that could support heavy equipment, accommodate electrical systems, and provide comfortable working conditions for personnel stationed for months or years. The framework approach delivered all of this. Maintenance crews could access the ribs for repairs, electricians could run conduit along the framework, and the rigid structure meant interior walls and equipment mounts could be installed anywhere, without worrying about load distribution. But this same sophistication required both components to remain intact. If the framework failed, the panels became just loose sheets of metal with no structural capacity. If panels failed, the framework stood exposed to weather, accelerating its own deterioration. The system had no redundancy. Every component was essential, which meant any component's failure threatened the whole structure. Peter Nissen's 1916 design had no such vulnerability. His corrugated sheets were simultaneously walls, roof, and structure. When you bolted them together, you created a continuous shell where every panel supported every other panel. There was no framework to rust out, no ribs to weaken, no separation between load-bearing elements and weather protection. The structure was monolithic. This difference meant nothing during the first 20 years. Well-maintained Quonset huts with intact frameworks performed flawlessly. But maintenance ended when the structures became surplus, and that's when the clock started ticking on structural failure. What happens when framework dies? In 1968, a farmer outside Cedar Rapids, Iowa, bought a surplus Quonset hut for machinery storage. For 15 years, it worked perfectly. Then, in 1983, during routine equipment moving, a tractor bumped one of the internal arch ribs. The rib, rusted at its base where water had pooled for years, cracked. The farmer didn't notice. Why would he? The corrugated panels still looked fine. Over the next 2 years, that single broken rib shifted load to adjacent ribs. They began bending slowly, invisibly inside the walls. By 1985, 4 ribs had failed. That winter, snow load collapsed the entire structure in one catastrophic failure. One moment it stood. The next moment, 20 tons of steel folded inward like a crushed soda can. This pattern repeated across thousands of Quonset huts through the 70s and 80s. Framework rust was invisible until sudden failure. And because the corrugated panels weren't structural, they couldn't compensate when ribs failed. They just went along for the ride, collapsing inward when their support disappeared. Nissen huts had no internal framework to fail. When corroded sections weakened, adjacent panels carried increased load automatically. The structure degraded gradually, visibly, giving owners decades of warning. A Nissen hut didn't collapse suddenly. It sagged slowly over years, remaining functional until the last possible moment. This graceful degradation was an unintended consequence of the design's simplicity. Because each panel overlapped the next by 3 inches and bolted through 3 layers of metal, load paths were distributed across the entire shell. When one bolt rusted through, surrounding bolts compensated. When one panel corroded completely, adjacent panels bridged the gap. The structure was fault-tolerant not by design, but by the mathematics of continuous shell construction. Engineering professors in the 1970s began using Nissen huts as examples of redundant structural systems, the kind of design where multiple load paths existed for every force. Students learned that redundancy was the key to long-term survival in structures that wouldn't receive maintenance. The Nissen demonstrated this principle accidentally, while the Quonset demonstrated its absence deliberately. The insulation time bomb. American engineering's greatest comfort feature became its longest-term liability. Every Quonset hut included fiberglass insulation sandwiched between exterior steel and interior plywood. This kept interiors comfortable, but it also trapped moisture. And moisture trapped against steel does only one thing: it rusts. The problem started at the bottom, where condensation inevitably accumulated. Water vapor from breathing, cooking, heating worked its way through interior plywood seams, hit the cold exterior steel, condensed, and dripped down inside the wall cavity. The fiberglass insulation acted like a sponge, holding water against the steel ribs month after month, year after year. By the 1970s, Quonset huts showed a consistent pattern. The bottom 3 feet of arch ribs were severely corroded, while upper sections remained intact. This bottom-heavy rust was catastrophic because it attacked the ribs exactly where they bolted to foundation plates, the critical load transfer point. When those connections failed, entire frameworks collapsed. Nissen huts, with their single-layer construction, never trapped moisture. Rain hit the exterior and ran off. Interior condensation formed on visible surfaces where it either evaporated or dripped onto floors. There was no hidden rust eating through structural members. Every corroded spot was visible, accessible, and could be patched with roofing tar if anyone cared enough. The British Agricultural Survey of 1978 documented this difference quantitatively. Of 847 World War I-era Nissen huts still in farm use, 89% remained structurally sound with visible surface rust but intact shells. Of 1,240 surveyed World War II-era Quonset huts, only 34% remained fully intact. 41% showed framework damage requiring repair, and 25% had already collapsed or been demolished as unsafe. The geographical distribution told its own story. Nissen survival rates were nearly uniform across Britain, from wet Cornwall to dry Norfolk, from mild Devon to harsh Scottish Highlands. Climate differences affected appearance, but not structural viability. Quonset survival rates varied wildly by region in America. Dry southwestern structures lasted longer, humid southeastern huts failed faster, and freeze-thaw Midwest installations showed the worst survival rates. The Quonset's complexity made it environmentally sensitive in ways the Nissen's simplicity avoided. Insurance companies noticed this pattern by the mid-1970s. Several regional agricultural insurers in the American Midwest began excluding coverage for structures over 30 years old if they were Quonset-style buildings, citing catastrophic collapse risk. The same insurers had no such restrictions on older barn structures or simple metal sheds. The Quonset's reputation as a collapse hazard became industry knowledge even before academic studies confirmed the framework failure patterns. The bolt count curse. A 40-foot Quonset hut used over 700 bolts and screws. A comparable Nissen hut used approximately 200 bolts. This wasn't just a construction speed difference, it was a long-term failure point difference. Every bolt was a potential rust site, a stress concentration, a place where the structure could begin falling apart. Quonset framework assembly required precise bolt tension, too loose and ribs shifted under load, too tight and threads stripped or bolt heads sheared. In 1943, with military specifications and regular maintenance, this worked fine. By 1980, with decades of thermal cycling, rust and zero maintenance, bolt connections were failing wholesale. The self-tapping screws attaching corrugated panels to Quonset frameworks presented special problems. These screws, driven through thin steel into steel ribs, created galvanic corrosion cells. Dissimilar metals, moisture, and electrical current from the junction accelerated rust at every screw hole. By the 1970s, windstorms were literally blowing panels off Quonset huts because screws had rusted away to nothing, leaving panels hanging by just a few remaining fasteners. Nissen bolts went through 3 layers of corrugated steel, panel to panel to panel, creating mechanical locks that remained functional even when rust reduced bolt diameter by half. The overlapping panels supported each other independent of bolt condition. Engineers called this redundant load path design. Farmers called it bulletproof. Foundation dependency. Quonset huts required foundations. The steel arch ribs needed to bolt to something solid, typically concrete pads or heavy timber plates anchored firmly to prevent movement. This foundation dependency created cascading failures decades later when foundations degraded. The foundation requirement stemmed from the framework design. Each arch rib concentrated enormous load at its 2 base points. A 40-foot Quonset in snow country might carry 15 tons of snow load, all of it channeled through 14 arch ribs to 28 bolt points on the foundation. If any bolt pulled loose or any foundation section settled unevenly, the entire framework geometry shifted. Ribs twisted, loads redistributed, and stress concentrations cracked welds at the connections. Wooden foundation plates rotted. Concrete pads cracked and shifted with frost heave. When foundations moved even slightly, they put torsional stress on the bolted rib connections. Those connections, already weakened by rust, failed. Ribs twisted, frameworks racked, and structures collapsed. Military construction teams in 1943 built Quonset foundations to specification, typically pressure-treated 6x8 timbers on crushed stone bases or poured concrete pads with embedded anchor bolts. These foundations, when properly maintained, lasted decades, but civilian buyers in 1946 often didn't follow specifications. A farmer wanting quick storage erected a Quonset on whatever level ground existed, sometimes using railroad ties instead of proper foundation timbers, sometimes setting it directly on packed earth with minimal preparation. 30 years later, when improvised foundations had rotted through or shifted, the framework had nothing solid to anchor to. Structures tipped over in storms or collapsed under snow loads because their bases had literally disappeared. A 1981 structural engineering study in Wisconsin examined 43 collapsed Quonset huts and found that 31 of them, 72%, showed foundation failure as the primary cause. The frameworks were often still intact after collapse, simply folded in on themselves when the base anchorage disappeared. Nissen huts were foundation optional by design. The corrugated panels could bolt directly to wooden sleepers, packed earth or even sand with stability coming from the continuous shell rather than anchored attachment points. When sleepers rotted, the shells remained self-supporting. A British agricultural report from 1969 documented a Nissen hut in Aberdeenshire whose timber base had completely disintegrated, leaving the corrugated shell sitting directly on dirt. It remained weathertight and functional, holding hay bales 43 years after construction. The physics behind this worked because of load distribution. A Nissen hut's weight and contents were spread across the entire circumference of the base, like a barrel sitting on its side. No single point carried excessive load. If one section of base settled, the shell flexed slightly and redistributed force to more stable sections. The structure tolerated differential settlement that would destroy a framework-based building. This foundation flexibility saved countless Nissen huts over decades. Agricultural land settles unevenly as organic matter decomposes and soil compacts. Buildings that require rigid foundations crack and fail. Buildings that can move with the ground survive. By the 1980s, British structural engineers were documenting Nissen huts with bases that had settled as much as 14 inches on one end while remaining structurally sound. The shells had simply deformed into slightly egg-shaped profiles, still weatherproof, still functional, just visibly lopsided. Quonset huts couldn't tolerate that kind of movement. A few inches of differential settlement was enough to bend arch ribs beyond their elastic limit, creating permanent deformation that concentrated stress and led to eventual cracking. Foundation stability wasn't just recommended for Quonsets, it was absolutely required, and that requirement meant decades later, when foundations inevitably degraded, the structures had no survival strategy. The standardization trap. American mass production made Quonset components perfectly interchangeable, which was magnificent for wartime logistics and deadly for long-term survival. Every 40-foot Quonset used identical arch ribs bent to exactly the same radius. When one rib failed, replacement required that exact component. No substitution possible. By 1970, nobody manufactured Quonset ribs anymore. Military surplus had dried up. When a rib failed, owners had three choices: scavenge parts from another deteriorating hut, fabricate a custom replacement at machine shops for hundreds of dollars, or abandon the structure. Most chose abandonment. Nissen huts were never standardized in the same rigid way. Field crews bent corrugated sheets to approximately the right curve and made them fit. Panel widths varied. Overlap distances differed. Bolt patterns were irregular. This drove American engineers crazy, but it meant Nissen repairs could use any corrugated roofing material available at local hardware stores. Farmers patched holes with mismatched panels, uneven overlaps, and improvised fasteners. The structures accepted repairs because they'd never demanded precision in the first place. A Yorkshire farmer interviewed in 1982 described maintaining his 1918 Nissen hut. Over 64 years, he'd replaced approximately one-third of the original panels using whatever corrugated metal was cheapest when repairs were needed. Some panels were galvanized steel, some were aluminum, some were painted iron. The structure didn't care. It held together because the curved geometry was forgiving and the panel-to-panel bolting created continuous support regardless of material variations. This repairability extended the practical life of Nissen huts far beyond their designed lifespan. A structure that could accept mismatched replacement parts meant owners could maintain it indefinitely using materials from hardware stores, salvage yards, or other deteriorating structures. The repair knowledge was simple enough that farmers handled it themselves without contractors or engineers. Quonset repairs required professional help in most cases. Replacing a damaged arch rib meant unbolting and removing exterior panels, extracting the compromised rib without damaging adjacent ones, fabricating or locating an exact replacement, installing it with precise alignment, then reattaching panels. Few farmers had the tools, skills, or patience for this work. Most just patched leaking panels with roofing tar and hoped the framework stayed intact. When frameworks failed, there was no simple fix. Climate and corrosion. The American Midwest proved uniquely hostile to Quonset huts. Freeze-thaw cycles, high humidity summers, and temperature swings from -20 to +90 stressed the complex framework assembly far more than Britain's moderate maritime climate stressed simple Nissen shells. Winter was particularly destructive. Snow accumulated on Quonset roofs and melted during sunny days. Meltwater seeped through screw holes into the insulation cavity where it refroze at night. Repeated freeze-thaw cycles jackhammered apart the panel-to-rib connections. By spring, entire roof sections were loose, flapping in wind, pulling away from weakened frameworks. British climate, despite its reputation for dampness, rarely froze. Rain hit Nissen exteriors and ran off. The corrugated profile channeled water efficiently. Surface rust formed but progressed slowly because cycles of wetting and drying prevented sustained moisture contact. The 1980 Royal Agricultural College study measured corrosion rates on 40-year-old Nissen huts at 0.3 millimeters per decade for unexposed surfaces. Quonset framework members buried in wet insulation showed corrosion rates exceeding 2 millimeters per decade. Coastal installations showed the opposite pattern. Salt air destroyed exposed Nissen panels rapidly, but left framework-protected Quonset interiors relatively unscathed. This led to an odd situation in California where coastal Quonset huts survived longer than inland ones, not because the design was better, but because frameworks stayed dry in climate zones with minimal temperature cycling and low humidity. The Pacific Northwest presented yet another variation. Constant moisture without freeze-thaw cycles meant both designs rusted steadily, but neither experienced the catastrophic stress cycling that destroyed Midwest Quonsets. A 1987 survey of military surplus structures in Oregon and Washington found 40-year-old examples of both designs still functional, though Nissen huts showed more extensive surface corrosion, while Quonset frameworks remained surprisingly intact inside their protective panels. These regional variations proved that neither design was universally superior. Each had environmental conditions where it performed better, but the critical difference was failure mode. Nissen huts degraded predictably across all climates, allowing owners to monitor deterioration and plan accordingly. Quonset huts either survived well or failed catastrophically, depending on whether local conditions attacked their hidden vulnerabilities. The uncertainty made them fundamentally less reliable as long-term structures. The psychology of maintenance. Nissen huts looked like they needed maintenance. The bare corrugated exterior showed every rust spot, every dent, every degraded section. Owners could see problems developing and address them when convenient. A bucket of roofing tar and an afternoon's work patched holes before they became structural issues. Quonset huts looked fine until they didn't. The exterior panels appeared solid even when internal frameworks were collapsing from rust. Interior plywood hid deteriorating ribs. Owners assumed everything was fine because nothing looked wrong. Then catastrophic failure happened without warning. This visibility difference affected maintenance patterns dramatically. British farmers maintained Nissen huts casually but consistently, patching obvious problems as they appeared. American farmers saw perfect-looking Quonset exteriors and did nothing until snow loads or windstorms revealed that internal structures had failed years earlier. The military understood this psychological difference even during initial deployment. A 1944 Navy training manual for construction battalions included explicit warnings that Quonset huts required internal framework inspection every 6 months because external appearance didn't reflect structural condition. That guidance worked fine with military discipline and regular inspections. It failed completely in civilian hands where nobody opened walls to check hidden ribs. A maintenance study conducted by Iowa State University in 1979 interviewed 200 farmers who owned surplus Quonset huts. Only 3 had ever inspected internal framework condition. The rest assumed that intact exteriors meant sound structures. This assumption proved fatal in approximately 1/3 of cases over the following decade, as hidden framework failures led to sudden collapses that often destroyed equipment or livestock housed inside. The same study surveyed 150 farmers with Nissen huts and found that 87% had performed repairs, usually patching visible rust spots or replacing damaged panels. The maintenance wasn't scheduled or systematic, it was reactive and obvious. Something looked wrong, so they fixed it. This casual approach kept structures functional because there were no hidden problems waiting to surprise them. Insurance adjusters learned to distinguish between the two designs when evaluating agricultural property. By the mid-1980s, several major agricultural insurers had internal guidelines that automatically flagged Quonset huts over 30 years old for mandatory structural inspection before coverage renewal. Nissen huts faced no such scrutiny regardless of age. The industry had quantified what farmers knew instinctively. One design announced its deterioration, the other hid it until failure. What survives today? As of 2024, approximately 2,000 World War I-era Nissen huts remain in active use across Britain and Commonwealth nations. Most are over 100 years old. They store farm equipment, shelter livestock, and house workshops. Some are protected as historical structures, but most survive because they're still useful and haven't fallen apart yet. The survivors exist across remarkably diverse environments. Scottish Highland estates use them for equipment storage at elevations above 1,500 feet, where winter conditions are brutal. Welsh farms operate them as sheep shelters in regions receiving over 80 inches of annual rainfall. East Anglian agricultural operations store grain in them in some of Britain's driest, sunniest conditions. The design's environmental adaptability meant it survived wherever it was erected, regardless of local climate extremes. Some Nissen huts have found unexpected second lives. A recording studio in Cornwall operates inside a 1917 Nissen hut, prized for its acoustics. The curved metal shell creates unusual sound reflections that musicians find appealing for certain recording styles. A craft brewery in Yorkshire ferments beer in temperature-controlled Nissen huts from 1918, using the structure's natural insulation properties to maintain stable conditions. These adaptive reuses demonstrate that century-old temporary structures can serve purposes never imagined by their designers. Fewer than 500 original World War II-era Quonset huts remain in civilian use in America. The vast majority collapsed, were demolished as unsafe, or were scrapped when maintenance became impossible. The survivors are almost universally structures that received exceptional care, remained weathertight with intact roofs, or were located in climate zones that minimized framework corrosion. Many surviving Quonsets exist in the American Southwest, particularly in New Mexico, Arizona, and Southern California. The dry climate preserved frameworks that would have rusted through in humid regions. Some have been continuously occupied since the 1940s, serving as homes, studios, or businesses. These examples prove the design could last when environmental conditions were favorable and maintenance was consistent. But they represent outliers, not typical outcomes. The preservation community has recognized approximately 200 Quonset huts as historically significant, mostly at former military installations now operated as museums or parks. These structures receive professional maintenance and restoration that keeps them intact, but this curated survival bears little relationship to the design's natural longevity. Protected Quonset huts survive because organizations actively preserve them, not because they resist deterioration on their own. The difference comes down to design philosophy. Nissen asked, "What's the minimum structure that will survive maximum neglect?" His answer was a self-supporting curved shell with no hidden components, no trapped moisture, and infinite repairability using common materials. The Quonset asked, "What's the maximum comfort we can engineer into temporary housing?" The answer was objectively better architecture that became objectively worse heirloom structures because complexity created vulnerability and improvement created failure points. The lesson nobody learned. Military engineers continue designing improved temporary structures, more comfortable, more capable, more sophisticated than previous generations. These modern systems use advanced materials, complex frameworks, and integrated systems that would amaze 1940s designers. They also cost exponentially more, require specialized parts, and won't survive decades of neglect because they're not designed to. They're designed to be excellent for their intended purpose, then disposed of when that purpose ends. The modern military's deployable rapid assembly shelter system, introduced in the 2000s, exemplifies this continued trajectory toward sophistication. These structures use lightweight aluminum frameworks, insulated fabric panels, and integrated HVAC systems. They deploy faster than Quonset huts and provide far superior comfort. They also cost approximately $85,000 per unit compared to the inflation-adjusted $12,000 a Quonset cost in 1943, and they're designed for a 10-year service life before requiring complete replacement. Nobody designs for century-long survival anymore because military doctrine assumes temporary structures will be temporary. The idea that a field structure might still be useful 80 years after deployment isn't part of modern planning. This makes perfect sense for military purposes, but creates problems when these structures inevitably enter civilian use as surplus. Current military surplus from Iraq and Afghanistan withdrawals includes thousands of modern shelter systems that civilian buyers are discovering cannot be maintained outside military supply chains. Specialized aluminum extrusions, proprietary connector systems, and integrated components from defunct manufacturers mean these cutting-edge 2010 structures are becoming useless in 2024, just 15 years after manufacture. The progression from Nissen simplicity to Quonset complexity to modern sophistication has created structures with ever shorter practical lifespans. Nissen huts were designed to be impossible to kill. That wasn't the goal. It was just what happened when you made structure and skin the same component, eliminated hidden failure points, and used materials that degraded visibly over decades instead of failing suddenly after years. The accidental longevity came from decisions Peter Nissen made in 1916, not because he was thinking about century-long survival, but because he was eliminating everything that could go wrong during rapid construction by unskilled labor in combat zones. Every feature that made Nissen huts fast to build also made them impossible to kill. No framework meant nothing could fail inside walls. Overlapping panels meant redundant load paths existed everywhere. Visible exteriors meant deterioration announced itself. Simple geometry meant repairs could use any available material. These same features made Nissen huts uncomfortable, cold in winter, hot in summer, and acoustically terrible. Military personnel complained about them constantly during both world wars. Architects dismissed them as ugly industrial sheds unfit for human occupation. But none of that affected structural survival, and structural survival was the only measure that mattered when counting decades instead of deployment cycles. The curved corrugated shells still standing after a century aren't better architecture than the Quonset huts that fell apart after 40 years. They're worse architecture. They're cold. They're loud in rain. They drip condensation, and they look like industrial sheds because that's exactly what they are. But they're still standing, and that's the only measurement that matters when you're measuring in decades instead of deployment cycles. Britain's Nissen huts outlasted America's Quonset huts because sometimes the best engineering is the kind that refuses to fail, even when it should have failed decades ago. The numbers tell the final story with brutal clarity. In 1946, approximately 15,000 Quonset huts entered civilian use in America. By 2024, fewer than 500 remained functional, a survival rate under 4%. In 1918, approximately 100,000 Nissen huts were scattered across Britain, Europe, and Commonwealth territories. By 1946, perhaps 30,000 remained as agricultural structures in Britain alone. By 2024, at least 2,000 were still in use, representing a survival rate over 6%, despite being built decades earlier under wartime expediency with inferior materials and minimal quality control. The last laugh belongs to Peter Nissen. His crude, corrugated sheds, dismissed as temporary wartime expedients, outlived the supposedly superior American improvements by generations. Not because his engineering was more sophisticated, but because it was more simple. And in structures meant to survive neglect, simplicity doesn't just work better, it's the only thing that works at all. Agricultural historians documenting rural building evolution note that the Nissen hut achieved something no architect intended. It became a permanent fixture by being aggressively temporary. Because it was never meant to last, nobody built planned obsolescence into the design. Because it was meant to be erected by amateurs, nobody created dependencies on professional maintenance. Because it was meant to be cheap, nobody used materials or methods that couldn't be replicated with common supplies. The Quonset pursued excellence and achieved it, creating superior temporary structures that served their intended purpose magnificently. But excellence in temporary structures created permanent dependencies that made long-term survival impossible. The Nissen pursued adequacy and achieved immortality by accident, creating crude temporary structures that refused to die because nobody had designed them carefully enough to fail properly. In the end, the lesson isn't that simple designs are better. It's that designs meant to be temporary should never be more sophisticated than they need to be, because sophistication creates failure points that matter only when time scales exceed design intentions, and time always exceeds intentions, always.